In this video, we're going to be talking about the methods of analysis for quantitative data. So first off, what are quantitative data? Well, quantitative data are what it says here is numerical representations of the observations in the social world. What that really means is we're attaching numbers to something we see in social life, right? And what we're trying to do is essentially both describe and explain what's going on in the social world. And instead of sort of pulling out meaning or experiences or feelings or attitudes or beliefs like qualitative data would do, quantitative data instead convert those to numbers, right? So whereas in qualitative data you'd really sort of talk to someone or read the text of an interview or read the text of a biography about how somebody feels about protests, and you would sort of read through that and try to pinpoint themes that are popping out. On the quantitative side, you can also look at themes that are popping out in someone's text, but instead of saying they said, social ties were important, or they said that biographical availability or having time to protest was important for actually protesting. Instead of saying those things, you say, did they say that social ties are important? Yes or no? And instead of saying yes or no, you give that, a number, 1, right? Or how many times did they say social ties were important? Well, across that whole interview or across the whole corpus of text, we see that they said something about social ties 10 times, right? So we can actually attach numbers to those same kind of base raw data, converting it to a quantitative form. So the actual process of coding in quantitative methods is assigning numbers to various attributes of the variables that we're looking at. So we can look at attributes or variables such as age or sex or political affiliation or socioeconomic status and see that we can attach numbers to those things, right? For example, if we look at age, we can measure it as, somebody says they're 1 year old, although they would not be taking a survey, right? Someone's 2 years old, they say they're 2, 3 years old, 3, so on and so forth. Or you can, because we're dealing with interval ratio level variables or variables that have numbers assigned to them, we may want to group those numbers into larger categories, right? Those attributes into larger categories, right? So we can say anybody less than 18, they get a 1. Between 18 and 24, they get a 2. 25 to 29 gets a 3. 30 and plus gets a 4, right? Either way, in the above version, where we're attaching the exact number to the exact age, or here, the below version, where we're attaching a number to a grouping of ages, either way, the outcome is the same, right? The result is we've assigned numbers to the right-hand column. Sex. Instead of saying male, female, other, we can assign numbers to those categories, those attributes, right? Female equals 1, male equals 2, other equals 3. We could even do what we call a dichotomous variable or a binary variable, a series of binary variables. Instead of saying female equals 1, male equals 2, other equals 3, we can say, well, let's create a variable called female, right? So instead of calling the variable sex and having 3 attributes, we can create a number of different variables that can be clustered into the sex variable, right? So instead of saying sex, we create a variable called female where the attributes are yes or no, 0 or 1. So does somebody identify as female? Yes or no? Then we create another category called male, right? Or another variable called male. So now instead of one variable, sex, with 3 attributes, we have one variable female with 2 attributes, yes or no, 0 and 1. The next variable, male, with 2 attributes, yes or no, 0, 1. And then we have an other attribute, right? So our other variable, we can throw an other variable there and say 0, 1. Do you identify as other? Yes or no, 0, 1. The important thing about what that is, like I said before, it's called a dichotomous variable or a binary variable. It's called dichotomous or binary because of two. You have two options, yes or no. Converted to numbers, yes usually equals 1, no usually equals 0. When we're creating dichotomous variables or binary variables like this, creating a bunch of 0, 1 categories or 0, 1 variables, we create a certain number of variables. The number of variables that we create based on the larger variable category is k minus 1 number of variables. So again, we have the sex variable, and let's say that k here, k minus 1, is the number of attributes, right? So we have one variable with 3 attributes. So if we wanted to convert these to a series of dichotomous variables, we'd say k attributes is 3, k minus 1 is 2. So what would happen is we would create 2 new variables. Instead of one variable sex with 3 attributes, we'd have one variable called female with 2 attributes, yes, no, 0, 1, and another variable called male with 2 attributes, yes, no, 0, 1. Why don't we need to make a third category? Why do we say k minus 1, or the number of attributes, the number of variables that we're making is going to be equal to k minus 1, the number of attributes in that first variable minus 1. Why do we do that? Well, let's assume somebody identified as other. We create a variable called other, their value would be 1, correct? If they identified as other. When we make 2 variables, right, let's say we make the female new variable 0, 1 and the male new variable 0, 1. Somebody who identifies as other, how would they be identified across these 2 variables? They would, or we could identify them by if they get 0 on female and 0 on male. This idea of k minus 1 for creating dichotomous variables based out of larger variables, this idea is based on what we talked about earlier with mutual exclusivity, right? If you get a 1 here, you are automatically excluded from the male variable and the other variable, right? If you get a 0 on female and a 0 on male, that means you don't identify as female or male, but that means you identify as something else, right? So that would be other. So the concept of mutual exclusivity is very important when it comes to these dichotomous variables, these series of dichotomous variables. Let's take this idea of political affiliation next. We have one variable with 4 attributes. If we wanted to create a series of dichotomous variables, how many would we need? Well, we would need k, the number of attributes, minus 1 number of variables total, right? So k, here we have Democrat, Republican, Independent, other. We'd have 4 attributes, meaning we would need k minus 1, 4 minus 1 is 3. We would need 3 new variables. What would they look like? Oftentimes it'd be Democrat, yes or no, Republican, yes or no, Independent, yes or no, and then we're good. Because anybody who got 0 on Democrat, 0 on Republican, 0 on Independent, they'd automatically be assumed, because of the concept of mutual exclusivity, that they have a 1 on the other category. So with political affiliation, we can assign numbers, right? These numbers don't mean anything, but we can assign numbers to them, right? This kind of harkens back to that idea of checking the code book, right? If somebody says, I voted Democrat in the last election, but the code there is 1, you wouldn't know that without looking at the code book. And next we have socioeconomic status. We can attach 1 to working, 2 to middle, 3 to upper middle, 4 to the 1%. Again, I talked about the concept of the code book. It's a document that lists the assignments of codes and attributes, or to the attributes composing these variables, meaning that it lists out the various codes and those code labels, right? So here we have an example. I know it's kind of cut off here, but just to give you a picture, this variable AGR1. The variable name is AGR1. That means if we looked in an Excel spreadsheet we'd have observations on the rows, right? We remember that. So every person or every case is on the rows, but the variables are on the column. So it would say ID is one variable. The second column, one of the columns would be ext1. The next column would be agr1. And agr1 stands for I see myself as critical, quarrelsome, right? So these are questions that are being asked of the participant, and they have to say, do I agree or disagree to this statement? And it's not just agree or disagree, they have the option to select. So these are the various attributes that could exist in the variable agr1. They can get a 1, they could select I strongly agree with that statement, I agree, slightly agree, I'm neutral on that statement, I slightly disagree, and strongly disagree. So higher scores on this variable indicate more disagreement. So if you went there and, row 17, meaning observation number 17, or actually observation number 16, because you have a title row, a header row. This observation has the number 5 for the AGR variable. So what that means is when they were asked to respond to agreement or disagreement to the statement, I see myself as critical, they say, well, I strongly or slightly disagree with that statement because I give a 5. This is very important for us to figure out what's going on in a data set, especially if you're working with secondary data from a website, a government-owned website or Pew Research Center, various research firms. You need the codebook to tell you what exactly is going on in the data set. Here's another example of a codebook, right? We have a variable from the GSS. The GSS is the General Social Survey. It's been administered every few years with various questions from 1972 to about 2018, I think was the most recent one. Maybe 2016. But here are two variables from that data set. It's called poll views and attend. So the poll views variable says we hear a lot about talk about liberals and conservatives. I'm going to show you a 7-point scale in which the political views that people might hold are ranged from extremely liberal, 0.1, to extremely conservative, 0.7. Where would you place yourself on this scale? All right. So poll views is basically asking them, do you identify as extremely liberal, slightly liberal, moderate, all the way through extremely conservative? And then you see 8 and 9, which are don't answer, or don't know and no answer. Right? Same thing for how often do you attend religious services, the attend variable. So in your code book, it was going to give you the text of that question, right? It'll say poll views is the variable name. The actual question text will be listed. The options or attributes that could possibly be selected are listed there. Oftentimes it's gonna say 1 to 7, like it says here, 1 to 7, but it's not gonna say don't know, or it'll say don't know, but if they don't answer, they just won't answer. Here's another one. So here's the attend variable. So I take that from the last slide and I just kind of highlight the various attributes or the various important parts of the codebook. We have attend listed here. That's the abbreviated variable name. We have how often do you attend religious services? That's the definition of the variable. We have variable attributes, 0, never, less than once a year, about once or twice a year, all the way up to don't know and no answer. Here, we've attached numerical labels to these attributes, right? So if I ask somebody, I gave them the attend variable, and I asked them how often do you attend religious services, and I see in the data set that for the attend variable they have 7 listed there. Does that mean they went 7 times? Or 7 times a week? Or 7 times a year? No, what that means is, let's look at the numerical label for the variable attributes. We see that 7 indicates every week. All right, so it's not several times a week, it's every week. So it gives us some indication. Levels of measurement, these are very important. When you move forward into the quantitative methods class, you'll need to know these levels of measurement because it's going to sort of identify or point you towards the kinds of tests that you need to run, whether you're going to do bivariate tests or multivariate tests. So levels of measurement are how we can assign numbers to variables, right? So nominal variables. We have three of them: nominal, ordinal, and interval ratio. Nominal variables have attributes that just classify but cannot be ranked, right? These attributes only have the characteristics of exhaustiveness and mutually exclusiveness, or mutual exclusivity. These are just simple categories. So something like religious affiliation, college major, hair color, birthplace, right? Political affiliation, right? While we can assign numbers to them, like we did for political affiliation, we know that these only have attributes that can be classified but not rank ordered. So something like political affiliation, where you say, I'm a Democrat, I'm a Republican, I'm independent, I'm other, I'm green, right? All these things, they are categories, right? They're attributes that people can select, but you can't rank order them. You can't say Republican ranks higher than independent, ranks higher than other, right? There's no numerical association, right? You can't rank order them. You may subjectively like to rank order them, but there's no inherent rank orderedness to those categories. Next, we have ordinal variables. Ordinal variables are those that classify but can be logically rank ordered, right? Ordinal, ordered, right? So nominal, all you can do is say, I belong to this category or the other one. One's not better than the other. Rank ordered, or ordinal variables, can be rank ordered. So something like socioeconomic status, right? You can be upper class, you can be middle class, you can be lower class. If somebody says, I'm middle class, you know that you're higher than working class or lower class. If somebody says I'm upper class, or the 1%, you know that they are higher than middle class, right? So you can rank order. But the important part is that ordered variables or ordinal variables lack an associated numerical value, right? So while we may say working class is number 1 and middle class is 2 and upper class is 3 or something like that, those numbers don't really mean anything, right? Does it just take one step to get to middle class and one step to get to upper class? We don't know what those steps mean, right? Socioeconomic status is based on education, occupation, income, all of these things, right? Social network, social capital, all of these things matter. So it's hard to associate a numerical value with the inherent rank orderedness of this variable, right? You can't say if I make $10,000 more, I'm going to be in the middle class. Well, is that 10,000 more to get to the middle class? Does it only take 10,000 more beyond that to get to upper class? Likely not, right? So although we may have numbers attached to them, there's no inherent associated numerical value. All we know is we can order them. And then finally, interval ratio variables. These classify, they can be rank ordered, and they actually have an equal numerical distance between them. So one step below is one less. One step above is one higher, right? One more. And the distance between these attributes have meaning, right? So a good example is temperature, right? We know that if somebody says, I live in Phoenix and it's 75 degrees right now, and somebody says, I live in San Diego and it's 76 degrees here, we know that Phoenix identifies as or is identified as 75. So that's their category. That's their attribute value. San Diego is identified as 76. So that's their attribute value, right? That's the category that they're in. We know that because there's a number attached to it, that 76 is higher than 75. And we know that San Diego at 76 is exactly 1 degree Fahrenheit more than Phoenix, right, in 75. Right? So again, nominal, they don't have numbers, they can't be rank ordered. Ordinal are just like nominal variables, but they have the added benefit of I can rank order them. And then interval ratio variables are the most sophisticated in that they have the characteristics of nominal and that they classify into groups. And they classify into groups that can be rank ordered. And why? So they meet the criteria of ordinal. And why is that? That's because 3, they have numbers attached to them. So if we look at our earlier examples, we can break down into various types of variables. Sex here is a nominal variable, even though we have numbers attached to it. That's because they're categories. One's not better than the other, right? Same for political affiliation. Socioeconomic status here is ordinal, right? We can rank order, but we don't know the distance between working and middle, and between middle and upper middle, and between upper middle and the 1% aren't the same, right? You might even say that the distance between upper middle and the 1% is much larger than the distance between working and middle. And then finally we have interval ratio, right? It has the characteristics of grouping, classification, categorization, right? If I'm 1, I'm in the 1 group. If I'm 2, I'm in the 2 group. If I'm 3, I'm in the 3 group. We know we can rank order because 3 is higher than 2 is higher than 1. And each step means 1 year, right? All right. Exhaustiveness and mutual exclusivity. What are these? So these are important characteristics to take into account when you're dealing with quantitative data or you're collecting quantitative data, right? Exhaustiveness just means that we're ensuring that all possible units can fall into a category, right? So we want to be able that we can handle missing responses, right? We want to provide the ability for everyone to identify as one category, right? So in the previous examples, for example, if we were looking at political affiliation, if I only provided the options of, so again, exhaustiveness and mutual exclusiveness really talk about the categories or the attributes that we're providing for our participants. Going back to political affiliation, if we only said Democrat, Republican, Independent, that wouldn't be an exhaustive list of attributes, right? And why is that? Well, what about people who identify as peace and freedom or American Independent, which is, by the way, different from independent? What if somebody identifies as green, right? By listing only Republican, Democrat, and Independent, you're leaving out other options that people could potentially select. So it's always very good to include like an other option, right? Say, Democrat, Republican, Independent, Peace and Freedom, whatever Roseanne Barr's party was that one year she ran, right? And then provide other, right? Because if there's a new party that comes up or springs up, you want people to be able to choose that category. Make sure all options exist, right? You want to exhaust all possible options. And then something that's mutually exclusive means that each unit, each person, each participant, each observation can only fall into one category, right? So you don't want somebody to be able to identify as both a Republican and a Democrat. Right? You don't want them to be able to identify as 18 and 22, right? So exhaustive, give them all possible options. And if you can't list all possible options, give them an other option. And then mutually exclusive means that make sure that they can only identify as one of those all possible options. I will make a note here that some things are important that they're not mutually exclusive. Things like race and ethnicity, right? We know that people identify as biracial, multiracial, multi-ethnic, right? So to say you should only identify as one is completely incorrect. So oftentimes you'll find on things like the census, which is coming out this year, you'll see instead of, select one that most identifies you, right? Select the race that you most identify with. It's sort of, select one that you most identify with plus select all others that you identify with, right? So it's basically a check mark system. It identifies this and this and this. All right, data entry, it's very important. And data analysis is also very important. So data entry, oftentimes when it's quantitative data, you're going to get things in an Excel format or a CSV, comma, separated values format. In this format, it's sort of just a very easy format for reading into data analysis software programs, right? Data analysis software. So the CSV is the sort of a universal method of data entry. If you're going out and doing a survey and you collect the data from those surveys and you're like writing down what person number one said for this question, that question, this, it's wise to just input those into Excel or to a spreadsheet of some kind, whether that's Google Sheets or something or Excel, and then you download those as a CSV because it's a very lightweight version of those data. Data analysis in quantitative data methods, there are a bunch, right? You may have heard of SPSS. A lot of sort of undergrad and some grad schools often use SPSS because it's very easy, point and click, right? The difficulty with SPSS is that it's expensive, right? If you don't have a site license through a university, then you're going to be paying hundreds of dollars per year for, I think it's around $400 or $500 per year for one license for yourself. And then you'd have to renew that every year. You can only work with one data set at a time, so one CSV at a time. Stata is another version that a lot of people like to use. Another package that people like to use, another bit of software. And Stata is a little bit more powerful. Well, it's actually tremendously more powerful than SPSS. It can do a lot of things, but now you can only work with two data sets at the same time. SAS is another old school program. I know people at the census, like a lot of workers at the census, use SAS still. Very much command line oriented. You could spend hours trying to clean up your code and it takes forever, and then finally at the end of 8 hours you realize you missed a period somewhere, right? You missed a comma somewhere. And then finally, the one listed here first is R. So whereas Stata, SPSS, and SAS are highly expensive and can only do certain things and can only work with 1 to 2 to maybe 3 data sets at a time, R is open source, meaning it's free, meaning there's a community of researchers and scholars and R users, working to improve and develop components within R. I already mentioned it's free, and you can work with, because it's object-oriented programming, you could work with multiple different objects or data sets. So instead of reading in one CSV file or 2 CSV files or 3 of them, you could have hundreds, if not thousands, of CSV files that you're working at the same time on. All right, types of methods. So we have univariate statistics, right? We're just describing what's going on in a data set. Bivariate statistics, right? We're looking at relationships between 2 variables, variable. And then multivariate statistics, where we're looking at multiple variables and their relationships with one another. Univariate statistics really focuses on describing a single variable at a time. Univariate statistics really focus on 3 main things. We have central tendency, measures of central tendency, which is mean, median, mode. Measures of dispersion are also known as measures of variability. This is range, variance, and standard deviation. And then we have frequency tables, frequency distributions, and graphs. So measures of central tendency, briefly, we'll quickly go over this. We know that the mode is the most frequently observed value or attribute. We can calculate the mode, or the most frequently occurring variable or category, for all variable types, meaning we can calculate the mode for nominal, ordinal, and interval ratio variables. The median is the middlemost case, right? It's the 50th percentile, the point at which 50% fall above that case and 50% fall below that case, right? The middlemost point. The median is a little bit more sophisticated than the mode, and because of that, it requires a more sophisticated level of measurement. So while the mode can be used for all 3 variable types, the median can only be calculated for ordinal variables and interval ratio variables, right? Why is that? Well, let's think about it. Can you calculate the middlemost case for political affiliation, right? Somebody says, I'm Democrat, I'm Republican, I'm independent, I'm other. What's the middle case? We don't know, right? Because we can't rank order them and say this one comes first, then this one, then the third, then the fourth case, then we don't know what the middle is. However, if we had something like socioeconomic status, we say, here's somebody who identifies as lower class, then a lower class, then another lower class person, and then we had a couple of middle class people, and then we had one, upper/1% person, right? So because we can rank order them, we can figure out which person falls at the middlemost case. Then finally, the mean. The mean is also known as the distribution's average. The mean is computed by summing up the values of several observations and then dividing that by the number of observations. Because it's the most sophisticated measure of central tendency, it requires that we use the most sophisticated level of measurement, which is interval ratio variables. So we can only calculate the mean if we have variables that have numbers attached to them, and we mean numbers that mean something. Here's an example, right? We can calculate the mode for something like age, right? We can see which category has the most number of people. For the variable age, we can also calculate the median, right? Find the middlemost point. And we can also calculate the mean, right? So we have the mean, we have the median, and we have the mode listed there. Next, we have measures of dispersion or measures of variability. Why do we need measures of variability? Well, if we look back, first let me say that measures of variability are only required, or you can only calculate measures of variability for interval ratio variables. So we want to be most sophisticated when we're describing what's going on in the distribution, when we're describing what's going on with one variable. So we can use the mean, the median, or mode. But the mean is most sophisticated, so we want to stick with the mean. Beyond the mean, we want to get measures of spread, right? What I mean by that is, are most cases very close to that average or very close to that mean? Or are they more spread out, further away from the mean? Why do we need to know that? Well, one example is that I use in my classes sometimes looks at the mean of the temperature across a year for two cities. We look at the mean for Phoenix, we look at the mean for Honolulu, Hawaii. And we look at those means and they both are 75 degrees. Assuming they're both 75 degrees, we also know that in Phoenix it gets much hotter and it also gets much colder, right? The winter could be very cold in Phoenix, but the summers are very, very hot, right? Whereas in Honolulu, the temperature is more quote unquote temperate, right? Like it's very close to whatever that mean is, right? So while in Phoenix it gets very cold in the winter sometimes, and it can get very hot in the summer, year round in Honolulu, it's generally around 70 to 80 degrees, right? So the spread is much smaller in Honolulu than it is in Phoenix, right? And because of that, we need measures of spread, right? We can have two distributions with the same mean, but those distributions could look drastically different, right? So we say, let's look at the range. We know what the range is. The range looks at the distance between the highest number and the lowest number. The problem is, when we look at the highest number minus the lowest number, or the range, that number is going to be sensitive to extremes, right? If we look at something like income, we could look at somebody's income and see, okay, there are a bunch of people who have zero income, and you have, if we include wealth on top of that, we can say somebody's bringing in $1.3 million a year or $160 billion a year, right? Let's count that as income. There are higher no, right? So there are people on the low end of the distribution, people on the high end of the distribution. However, that one person making 160 billion a year, right? It's usually just one person. They are way far out from everybody else. So if we calculate the range, that range is going to be huge. That range is going to be 160 billion, right? It's sensitive to extremes. It's sensitive to outliers. So 0 and 160 billion are extreme outliers. So what do? Instead of looking outward towards the tails of the distribution, the ends of the distribution, and subtracting them, we can calculate what we call variance and standard deviation, right? So we can look inward and we say, where's the mean, and are these scores clustered or really close to the mean, or are they further away from the mean, right? So the mean becomes our starting point, not the tails, not the extremes. So variance is a measure of dispersion around the mean, but it's in squared units. And then the thing that we usually want, or most often want, is standard deviation. Standard deviation is the number of, basically we can say, it's a number of units around the mean. We can use the standard deviation to say, if we know what it is, about 60 to 70% of cases fall within one standard deviation of the mean, 95% within 2, and 99.9 usually within 3 standard deviations of the mean, right? So the standard deviation is very helpful because it helps us break up a distribution. Instead of looking at the high end and the low end, we say, where's the mean, and can we take steps outside the mean, right? One step to the right of the mean, one step to the left of the mean, one step up, one step down from the mean, and then we split a distribution into 3 steps, right? 3 steps above and 3 steps below. Variance you can think of, I say in squared units, variance is just a step towards standard deviation. So standard deviation is the gold standard here. So why do we use standard deviation? Well, it gives us a measure of clustering around the mean, so how close or how far most cases are from the mean. For example, we have this. We have amateur golfer scores and professional golfer scores, right? We have amateur golfer scores mean of 100, professional golfer score of 70, right? So we see that the total score is lower for professional golfers, right? Meaning they're doing better, right? Whereas it's larger for amateur golfers, meaning they're doing worse, right? We also see we can take standard deviations and say, if we know that there's a distribution and we have a mean, we can say each one of these distributions can be broken up into 3 steps, right? 1 step above, 2 steps above, 3 steps above, 1 step below, 2 steps, 3 steps below, right? If we look, no matter what, 1 step below to 1 step above the mean is going to constitute 68% of the cases, whereas -1 and +1 standard deviations of the mean also counts up or covers 68% of the cases, regardless of the distribution, or regardless of the mean of the distribution, right? So the standard deviation is very helpful for us for describing what's going on in a distribution. Then we have graphing, right? So we can calculate a frequency distribution, right? Frequency distribution, say how many people said this, right? 1,359, 1,030 people said less than once a year, right? That they, go to church. So I think this is the attend variable from earlier. 1,132 people said, I go to church once a year, right? It gives you percentages, right? What percent of people said that? So on and so forth. That is a frequency distribution in table form. There's also a frequency distribution in histogram form. We have a pie chart. We've seen those before, right? Each slice represents a percentage of the total. And then we have bar graphs, right? We have bars, right? This person goes less than once a year. This person's once a year, right? We have a special case of bar charts called histograms. Bar charts are usually not supposed to be touching, but if they are ordinal or interval ratio variables, usually interval ratio variables, we can treat them as one step equals the same interval above or below. So when we have that, we have a special case of a bar chart called a histogram. So keep that in mind. Bivariate statistics. So this is where we're moving away from univariate statistics, or just describing what's going on, to bivariate statistics that help us examine actual relationships between two variables, right? So bivariate, two variables. Now we're getting away from descriptive statistics into inferential statistics, right? Explaining something about the social world, right? Generalizing to the social world. All right, bivariate statistics is an analysis of two variables simultaneously for the purpose of determining an empirical relationship between them, right? We want to generalize. In univariate statistics, we often can't generalize because we're describing just one variable. We're not describing how it's affected by, or how it predicts, or how it results from another variable, right? But when we start thinking about research questions about the social world, we need to start thinking about two variables at the same time and how they're related to one another. How's this X variable related to this Y variable, right? How are social ties related to protest participation, right? And we have 4 different bivariate tests. There are many more, but these are the 4 main bivariate tests. We have chi-square. Do not say chi. Do not say chi-square. It is chi-square, the Greek letter X, right? Chi. We have the t-test. So the chi-square is a measure of association. The t-test is a measure of mean differences between groups, right? You're looking at the mean for one group and seeing if it's different from or the same as the mean for another group, right? So we're looking at the relationship between group membership and their overall score or their means. The analysis of variance, or ANOVA, not ANOVA, ANOVA. ANOVA is very similar to the t-test. It's actually an outgrowth of the t-test. And the t-test, again, looks at, group membership, so group 1 and group 2, and how, whether or not the mean of group 1 is equal to or different from the mean of group 2. The analysis of variance says, well, sometimes we don't have just 2 groups. Sometimes we have 3, 4, 5, 15, 30 groups, and we want to see, does the mean of this group 1, is it the same as or different from all the other groups? Or is it the same as this other group but different from everything else, right? That's what the analysis of variance does. So it looks at group membership for 3 or more groups, and how their means are similar or different. Then finally we have correlation. Correlation is the measure of relationship or association between 2 variables, but it's looking at interval ratio variables, right? Does the effect of one influence or increase the effect of other, or decrease the effect of others? This will come in handy once you get to the next stats class, quantitative methods class. It'll help you figure out which kind of bivariate tests are going to be most important for answering your research questions, right? Here I've broken it down by the type of variable and whether or not it's an independent variable or a dependent variable, right? So here we see independent variable. We have a nominal independent variable, interval ratio independent variable. We have nominal ordinal dependent variable, interval ratio dependent variable. So if we have a nominal or ordinal dependent variable, so that's going to be our y variable, and a nominal or ordinal independent variable, our x variable, we should use a chi-square test, right? If we have an interval ratio y variable, or dependent variable, and a nominal ordinal independent variable, so an x variable that is nominal or ordinal, then we use a t-test or an ANOVA, right? So this is basically the group to which someone belongs, right? You are either Democrat or Republican or independent, right? And then you have a dependent variable that is interval ratio, meaning, I don't know, something like IQ score, right? That has numbers attached to it. We'd say we could use a t-test or an ANOVA. We could say, does the mean IQ score differ by political affiliation or group membership, right? So do Democrats have higher or lower IQ scores than Republicans? Or do Democrats have higher or lower scores than Republicans or independents or others, right? The important thing to remember here is, again, the t-test looks at mean differences for two groups only. You can only test two groups and their mean differences. Whereas ANOVA is an outgrowth and says, hey, sometimes we have more than just two groups. Sometimes we have 3 or 15, right? So again, t-test looks at only mean differences for two groups. ANOVA looks at mean differences for 3 or more groups. And then finally, I have the correlation, which is dependent variable that's interval ratio, and an independent variable that's also interval ratio, right? So let's say education and income. Education being years of education, right? Interval ratio, year 1 year, 2 year, 3 year, 4 year, 5 year, 30 year, right? And income, $1, $2, $3, $4, $5. We can look at a correlation to see, is there an effect of education on income? Here we have the sort of an interval ratio measure that's independent and a nominal ordinal dependent variable. That's not really a test in bivariate statistics. I mean, you can try to run a chi-square. I know there are some non-parametric tests that you can use. You might even sort of start thinking about logistic regression here, but that's sort of coming into the next phase where we're moving on from bivariate tests to multivariate tests. So keep this in mind. This table will help you. It'll go far for you or help you go far. On the course website, I've also posted a zip file with a bunch of different PowerPoint slides for practical guide that will cover this for each test. It'll say this is the breakdown, these are the assumptions of each test. And it also gives you the slides for chi-square, for t-test, for ANOVA, and correlation in there. So you can take a look at those to get more in-depth experience, sort of understanding what these tests are doing, to serve as a jumping off point for, the future when you're doing your capstone and other research projects. And then finally, multivariate statistics. So we're examining relationships between 3 or more variables for the purpose of inference, right? So univariate statistics, it's just describing, whereas bivariate and multivariate statistics are really looking to infer or generalize to the population. Right? The difference between bivariate and multivariate statistics isn't just that we're adding one variable, but we're sort of trying to reach that idea of causal relationships, right? The 3 criteria for causality in social sciences at its base level are an association, time ordering, and the absence of spuriousness, right? So it means association, there must be a bivariate relationship, right? X and Y, X must relate to Y, there must be an association, so there's a correlation or a chi-square relationship or a t-test relationship or an ANOVA relationship. That's the first criterion. Second criterion is time ordering, right? The X variable must come before the Y variable, right? X variable must precede the Y variable. So group membership must come before IQ score, so on and so forth. And then the final one is the absence of spuriousness. So the third one, absence of spuriousness. And to make sure that spuriousness doesn't exist, which again, to remind you, is if we throw in a third variable, the relationship between X and Y doesn't disappear, right? So that means to account for spuriousness, we also have to throw in a third variable and a fourth and a fifth, right? So multivariate statistics help us get closer to causality in social sciences. And very quickly, there are multiple tests that analyze relationships simultaneously by looking at a bunch of different variables. So you can have multiple independent variables with one dependent variable, right? So you have x1, x2, x3, x4, x5, x15, and then they're examining all their relationships with one another and all of their relationships with y, right, in tandem. So we have MANOVA, which is one test, right? It's multivariate analysis of variance. We can talk about RM ANOVA, which is repeated measures ANOVA, which is another type of ANOVA, but it's not really multivariate, but just so you know. The main thing we have for multivariate stats are regressions. So you've heard of regression to the mean, right? Sort of along those lines, right? We have multiple linear or OLS regression. We have bivariate regression, which could exist. We don't really cover that in this class, but when we're talking about multivariate statistics, we're going to be dealing with linear regression, also known as multiple regression, also known as OLS regression, which is known as ordinary least squares regression. So you can look all of those up and they're the same thing. We have binomial or binary logistic regression, where the outcome is a yes-no, 0, 1. Multinomial logistic regression, Poisson regression, which is a count regression, negative binomial regression, which is another count regression. We have event history / survival analysis and time series analysis. So event history meaning the time until an event happens, or the rate of failure or success of an event. And then time series, essentially analyzing the time, sort of a correlational look at how time affects relationships, right? And that is it. So now we know the various quantitative data analysis strategies